So for 12.1, it's going to be statistics. So some of you are going to take stats next, and I want to make sure you've got a little bit of an idea of what's coming because the first part of stats goes kind of fast. All right, so look at this. We are looking at sampling, like how do you collect your sample, frequency distributions. That's going to be like how often a number shows up in your data set, and graphs. So, what is statistics? Statistics is just that idea of collecting data, organizing it in some way. It could be a graph, it could be by its numbers, it could be by words, and then interpreting what you got. Okay, so there's a lot of gray area in stats. Okay, there's specific things that we learn that this is the way a statistician does it, right? But there's still like gray area with that interpretation piece as well. So descriptive statistics is where you're collecting, organizing, and summarizing. So, excuse my yawn. Descriptive statistics is what we will do the most in this class. Inferential is making generalizations about the data that you collected, like drawing up conclusions. So I just collected the data of, all the ages and the grades of people in my classes, and I compared them to each other. And I came up with a conclusion about it, right? That's inferential. So we don't have as much inferential in this class as you will in straight stats. Population. So what a population is it's all the people that you're talking about, or the thing, the area. So I could do a study about Sheridan, right? And then that is my population. I could do a study with the whole United States. That's my population. I could do a study with, just the college, and that's my population. Okay. A sample is a group that you pick from whatever that population is. So if I'm picking the college, a sample could be my classes. That's a sample. It's not a very good sample because it's not really random. It's, specific to me. But so when we look at a sample, representative sample, a sample that exists the representative sample, you can read that. That's not going to be something that comes up very much or very often at all. So look at this. Example one. A group of hotel owners in a large city decide to conduct a survey among citizens in the city to discover their opinion about casino gambling. What's our population? What's the big thing that I'm looking at? It's the city, right? So the it's the city, right? The population is the city and all the people in it, right? Okay, it is suggested to survey all people at six of the largest nightclubs in the city on a Saturday night about their opinion on gambling. Is this a good idea? So I'm going to go stand outside the nightclub and I'm going to ask people what their opinion is on gambling and having gambling. Is there a flaw in that way of sampling? So you might be like, no, great idea. Well, my brain goes, if I drink and I'm at a nightclub, I'm more likely to gamble. So you're really collecting a sample from people who are probably more likely to like gambling. Okay. You can't just, if you want to get a good sample, it needs to be random. It needs to be like, I went across the city, I picked all the addresses, and I did every 20th address across the city and I surveyed them. Or something like that. That's like a strategic way to do a sample. It's just so hard to get a good sample that when people tell me there's data on something, you need to be like, I want you to think, how did they sample? Right? Did they really get a random sample? Okay. So is this a good idea? It's biased. Okay. I go to Walmart. I stand outside the doors and I ask people their opinion. Is that a good idea? So instead of being at the nightclub where people probably like gambling more, I'm at Walmart, right? definitely better. But is it good? Does everybody shop at Walmart? Sheridan, probably, but does everybody in general in a large city shop at Walmart? No, it's not an equal chance for anyone in the city to be at that Walmart or to be at that nightclub. So it's not a real good setup. So it is biased um, as well, but it's still better than the nightclub. So here's the really, it is so hard to get your sample. It just is. It just is. There's no way around it. It's hard to get people to participate. It's hard to get a sample that is considered truly a random, simple sample. So I go through some like ways that you could, come up with. I thought there was a couple more. Nope, that's all. That you could come up with a random sample. You could identify each element in the population, assign a number to them, and randomly select the numbers. You could assign the elements of the population who have the number to your sample. So there's one way. I mean, really, like you could do the address like we talked about. You could do a survey sent to everybody's address. Problem is not everyone will respond. Okay, you see where I'm going. Lots of biased. Is there ever really a amazing sample? I don't know. I go towards nope. Okay, which of the following is the best way to select a random sample to find out how many citizens or how the city's citizens really feel? So which of the following is the best way? Oh my gosh, I'm so sorry. You're gonna laugh at all these videos because I'm either blowing my nose, sneezing, or yawning. I don't know. I'm going to make Math 1,000 videos, and that's the way it is. Okay, so the first one, a random survey, randomly survey people who live on the oceanfront condominiums in the city. Survey the first 200 people whose names appear in the telephone directory. No one even has a telephone directory anymore. Randomly select neighborhoods of the city, then randomly survey people within the selected neighborhoods. Which one sounds like you will get the best random sample? I hope you said C. Whoop. One, you're only doing one area of the city. Not everyone has a chance. You want everyone to have a chance. Okay. Number two, first 200 people. Well, my last name's an M. I'm out. Right. So not everyone has a chance. C, everybody has a chance to be in your sample. A much better sample. All right. Enough about samples. Okay. Gosh, the only time I could think of like samples in real life, like really affecting me was I am a cancer survivor. And when I got cancer, people would like, there's so much research about this or this or this, right? And then I would look it up and they had like 4 people in their study. I'm like, did you even look at what you're sending me? So think that through before you send somebody a study of something. Look at their sample. It better be freaking large, lots of people, and it really better be done well. Because if you don't get a good sample, I don't care what you did with your math, it's done, right? It doesn't matter. If that first piece isn't done well, nothing will be done well. Okay, so frequency distributions, we're going to move on. So now we've collected this data, and hopefully we've done it in a random way and the best we can. And each piece of data is a data item, excuse me. So each number you collect. And then a frequency distribution is just a chart with 2 columns, the list your numbers or your categories, and then how many of each one. That's all it is. And so frequency is just how often something occurs. So we're going to construct a frequency distribution of this data below. So this was actual grades of my last year's class. I meant to switch them to your class this year, but I didn't do it. I forgot. So these are last year's, so they're grades. So let's look at, for our distribution, we could do every single number has its own, or we could do a group of numbers. So grades naturally grouped A, B, C, D, F, right? Well, you could also maybe you're doing like I think that the homework has like a stress level from 0 to 5. So each 0, 1, 2, 3, 4, 5 could be its own category. So we're going to draw a line. We're going to have two categories. We're going to have our data, which is grades, and then we're going to have our frequency. Okay, so to get an A, right, you need a 90 to a 100 or 99, right? We'll do 90 to 99. The next one then be 80 to 89, and then 70 to 79. I kind of wrote that. Oh no, that's all right. 60 to 69, and 50 and to 0 below. We'll just do below 50 as its own group. When you get to stats, you won't be able to do 50 as its own group because under 50, because you have to keep the same width of your category. So you would have to do 50 to 59 and so forth, all the way down. So how many, I like to do two little lines here, bear with me. How many are in the 90 to whatever? Well, here's what I like to do, especially if you have a lot of data. I like a tally section. Okay, and this is a tally. So I'm going to go 81 is our first number. So I put a slash here, then 94, then 79, then 86, then 66, then 88, then a 90, then a 55, and then a 60, 75, and then 80, 80, 88, 74, 29, 32. So tallies, I can just go straight across, tally it up and be like, okay, there's 2 here, 6 here, 3 here, 2 here, 3 here. And that's my frequency. Okay, frequency total. And again, this could be like one number on each row, or it could be a group of numbers. Now, when you get to stats, you do this at a lot more specific level, but that's all we're going to do. What are some conclusions we can draw just from this one chart frequency table that I have? What are some things that we can draw from that? Well, I could be like, so the most common grade is between an 80 and 89 or a B, right? So 6 people are in that category. I can draw 3 people are not passing. Really 5 people because a D is not passing. Okay, those are the kind of conclusions you can draw for this part. Okay, construct a frequency distribution for the data showing final course grades for students in pre-calculus course listed alphabetically by student name in the gradebook. Okay, we can still do a frequency of words. This is not numbers. This is category data, qualitative data, not quantitative or numbers, right? So qualitative words, categories, words, right? And the other world is numbers and quantitative. We have so many things we can do with quantitative data, not with words or letters like this. So really, we're going to still do, our 2 lines, right? And we have our grades and we have our frequency. And we could do a tally section if we want. We have A, B, C, D, F. So really, this is the same, just with words. So we could do a little tally section just because that's easy. So we're going to go F, A, B, B, C, C, B, C, A, C, C, D, C. I almost lost my spot. B, D, C, C, B, C. Oof. Wow, lots of oops. I didn't do the 5 very good there on my B. That's okay. I didn't do it the right way. It's okay. 3, 5, 9, 2, 1. So there's our frequency of letters. We can still tell most people have a C in this class, right? So we can still get data from our category data or our words. Okay, group the frequencies into classes that are meaningful for the data. Since letter grades are given on 10-point scales, we can do the lower class and the upper and the class width. Okay, so For this, our lower class limit, let's go back up and just look at this. This is our lower class limit. Think about a class as just being your group. And what's the lowest you can be to still be in an A? Well, you could be at a 90, right? And really it does go to 100, but we don't like having I don't know. You'd have an extra number in that one if we did 100. Okay. So if we're talking the lower class limit, it is the lowest you could be. The upper is the highest you can be, and the width is the difference between each one. So on a 10-point ranges, you have 10 numbers between each category. The lowest being like your 90, the highest being your 99. 10 numbers: 90, 91, 92, 93, 94, 95, 96, 97, 98, 99. That's 10 numbers because 90 is a number. So the width is 10. Okay. I don't, we're doing another, I'm not going to do another one. I just like these definitions here. Okay. Lower, upper, they naturally make sense for grades too. Oh, right. So what if I take this frequency table, like right here, right? This frequency table, and I draw a histogram of it. I'm going to actually draw one to explain that type of graph before you just look at one. So I'm going to draw a histogram right here. But you should be able to fit it on the side. Okay, so a histogram shows frequency as well. And we're going to go 0 to 50. Gosh, that's going to be crap. I know that's kind of crappy because it's not equal, but that's okay. So then 60, 70, 80, 90, 100. So we're counting by tens because that naturally flows for this. 1, 2, 3, 4, 5, 6. And what you do up the side is frequency. Okay, so between 0 and 50, I have 3. I go all the way across, and that bar takes up that whole 0 to 50. I know I didn't do real 0 to 50, but I mean, I really probably should have done 0 to 10, 10 to 20, but you get the idea. So then 50 to 60, you don't include the first number here because that's included in the last group. No, it should go the other way. 50 to 60, I didn't even have that group. I did. Oops. I'm gonna change this to 59. We'll just pretend that's 50 to 59. So that would make it this group here. And I know it's not quite, but I don't like that erasing everything here. Let's go small. Whatever. Okay, and then 60 to 69. So 70 would bump us into that next category. So 60 to 69, we had 2. And so we go all the way across touching like that. 70 to 79 was 3. So we're going to go up to 3. And that whole box has got that. 80 to 89, we had 6. So we're going to go up and back down. 90 to 100 is 2. If we had something over 100, it would be its own box. That's a histogram of that data. So a histogram shows frequency and a frequency table shows frequency. So these show the same thing, just sometimes we like a graph better than we like the table. Same thing though, shows frequency. So go down here, you can see a histogram. So the key features really are that your bars touch and it's used to display frequency. So visually display the data. And then I want you to add shows frequency. Okay. So when we look at things like grades, we kind of look for it to be a bell shape because that is representing normal. We're headed that way. We're going to look at histograms and see if they're normally distributed. And so this graph it does go up as a bell and back down. So pretty symmetric on both sides. So we're headed that way eventually. For now, we're just going to look at the histogram. And this one shows the number of boys with maximum yearly growth. Oh, so this is just showing when boys grew the most. So it looks like 13 to 15 is the big years for growing. Okay, so this histogram is huge. I'm going to tell you, in the statistical world, this is big. And you could just start doing it on Excel, which is insane to me. And it's not even that great of a feature, like they need to work on it. Okay, frequency polygon is somebody who wants to make a weird different graph of the same thing. So they put a dot on the end in the middle of each box, right? And then they connect them. Frequency polygon. I don't really care. They show the same thing. And this would all be gone. Just the lines would show. So I don't know why it has both on there, but frequency follow is another graph that people like to make. Okay, I thought there were other graphs we go over. So if you have a bar graph, it looks like a histogram, but they're very different. A bar graph, each thing is represented on a bar. So we have to use a bar graph for category data for sure, because there are words like an A, there's 6 A's. We can't do a histogram because it can't go from this number to this number. So a histogram, I still think it's hilarious. I'm allergic to your class. So a histogram has to be numerical, qualitative. All right, then we're going to do stem and leaves. We have stems and we have leaves. Kind of just a way to put our data in like a category. So if I see this data down here, it's got 2 digits. So I'm going to draw a line, maybe if I have my drawer on, and I see 90s, 50s. Do I see 40s? Yep. So let's start with 90s. Now these are my stems. 80s, 70s, 60s, 50s, 40s. I don't think we have anything below. And what I do for this is I list the data. Like I don't want to write 91, 92, 93, and so forth. I like there's a 9, and then I just say the second parts of those 9s. So for the first number, 82, we would go to the 8 row and put a 2. So that represents 82. Then we have a 47, then a 75, then a 64, 57, 82, 63, 93, 76, 68, 84, 54, 88, 77, 79, 80, 94, 92, 94, 80, 94, 66, 81, 67, 75, 73, 66, 87, 76. This is a lot of data. You have 45, 43, 56, 57, 74, 50, 78, 71, 84, 59, and 76. Whoosh. So there's my stem and leaf. It still kind of shows frequency, like how common things are. You can see that it looks like there's more 70s than anything else. You can also put these in order if you want, but it doesn't really matter. This is just a way to organize your data for yourself. You might be given your data in a stem and leaf. Okay. The next part is such a big idea to me. Okay, I think that's right. Okay, and that is deceptions in your visual displays. Deception. So they collect their data in a crappy way and then they display it in a crappy way to you. And they make you believe that they did this study. They're going to cure my cancer from, I don't know. There were like tons of things that people listed. I probably shouldn't say them. Okay, so deceptive graphs can be distorted and can distort the underlying data so they can show the data the way they want. The graph on the left stretches the scale on the vertical axis to create an impression of rapidly increasing property rate. So let's look at these. These all show the same thing. And what they did here was they separated it off by barely any each time versus bigger here, so that this will show a bigger rise when really it's like pinching down and opening up that graph right here. So I could scroll in and make it look like, man, the poverty rates are just rapidly increasing. Or I could scroll out and be like, oh, they're not really growing that much, right? And then you have a table, and this is the actual data. So you have to be very careful of broken graphs not counting by the same number. So like maybe you go, I don't know if this one 11, 12, 13, 14, 15. No, that one counts correct. This one's weird. Yeah, no, this one doesn't count in a specific order. This one's weird. You need to go 1, 2, 3, 4, or 10, 20, 30, 40, or something in a specific order. It can't go 1 to 5 and then jump to 50 and then jump to 100. Like that's not counting in a consistent way. You could do a little broken thing and start at a certain number. That's pretty common. Still kind of misleading, right? These are misleading. So here's a list of things to watch for. Is there a title? Titles are big. Title what you're doing. Are numbers lined up with tick marks on the vertical axis with some kind of scale? Has the scale been varied to create more or less dramatic impression? So same thing we just looked at. Do too many designs or cosmetic effects draw your attention or distort your data? I had this one graph. Now I can't. I didn't put it on this one. I usually show it in my live class, but it has like a picture of a house like this and be like, in 1980, this was the size of the house and it was like 1,800 square foot. And then in 2000, whatever, here's the size. Oh man, that's a beautiful house. Here's the size of the house, right? So this one was like, oh my gosh, I'm usually better than this. My drawing is pathetic. And this is only 2,000 square foot. So it's only 200 square foot more for the more current one, but the picture shows like, holy cow, houses are way bigger than they were in the 60s when really they're not that much bigger. I think they truly are bigger, but that's just an example of what they could do to draw you in. I totally look at this graph and I think, wow, it's way bigger. And we could even label this like 2022, 1955 or something. I said 55 and wrote 50. Okay. So look for those kind of things. Here's a couple more graphs too. We can notice it is counting okay here, but it has a break here. And that allows for more of a dramatic drop. It's more like zoomed in. Okay. These ones are the same as well. Enrollment. Oh, they like totally didn't even label. You don't even know. Like it could be, they aren't really giving you good information there. You're like, wow, look at the differences, but it could be such a slight difference between each tick mark. Okay. So misleading graphs can really go anywhere, and misleading data is big. That's what this section talks about.